What if the same ideas that explain black holes and bending starlight also shape the behavior of electrons inside a tiny electronic chip? It may sound like science fiction, but researchers at the University of Geneva have uncovered evidence that something remarkably similar to Einstein's gravity exists inside certain quantum materials, not as a force, but as a hidden geometry that bends the paths of electrons. To understand why this matters, we need to look at where modern technology is headed. Today's electronics are built on our ability to control how electrons move. From the first transistors to modern processors, progress has always depended on understanding matter at smaller and smaller scales. But as we push toward ultra-fast computing, near-instant information processing, and electricity flowing with almost no energy loss, traditional models of physics start to break down. This is where quantum materials come into play. Quantum materials operate according to the rules of quantum mechanics, where electrons don't behave like tiny billiard balls. Instead, their motion is shaped by probabilities, wave-like behavior, and collective effects that only emerge when many particles interact together. Over the last few decades, physicists realized that when large numbers of electrons interact, an unexpected structure can appear, a form of geometry embedded in the quantum state of the material itself. This geometry doesn't exist in ordinary space, but in a more abstract quantum space that electrons move through. This idea is known as the quantum metric. Much like space-time curvature in Einstein's theory determines how light and matter move under gravity, the quantum metric determines how electrons travel through a material. It subtly bends their trajectories, alters how they respond to electric and magnetic fields, and influences key properties like conductivity and optical response. For nearly 20 years, the quantum metric was considered mostly theoretical, mathematically elegant, but extremely difficult to observe directly. That has now changed. The UNIGI team, working with collaborators from the University of Salerno and the CNR Spin Institute in Italy, detected this hidden geometry at the interface between two oxides, strontium titanate and lanthanum aluminate. This interface is already famous for hosting exotic quantum behavior. By applying intense magnetic fields, the researchers observed how electron paths became distorted. These distortions couldn't be explained by conventional physics alone. Instead, they revealed the influence of the quantum metric, a geometric structure shaping electron motion from within. This is the moment when theory becomes reality, says physicist Andrea Caviglia. What was once an abstract concept can now be measured, analyzed, and used. Even more surprisingly, the researchers showed that this quantum geometry is not a rare feature. It appears to be an intrinsic property of many materials, meaning it could play a role far beyond this single experiment. The impact could be enormous. With this new understanding, scientists can characterize materials with far greater precision, paving the way for electronics operating at terahertz speeds, trillions of cycles per second. It could also advance superconductivity, reduce energy losses, and deepen our control over light-matter interactions. In the end, one of Einstein's most profound ideas, that geometry shapes motion, may help define the future of electronics. Not in distant galaxies, but inside the chips powering tomorrow's technology.